This is what I would love, and I think you guys would all love this too. This is the future, and a future where everything is green and everyone gets along with each other and we're all happy and we have clean energy and no climate change. That would be awesome. Unfortunately, here's where we're at right now. We have a mess in several areas. And I think it's really a struggle to see that vision of where we're going with our energy system and our population growth and all the other issues facing us right now. In fact, there are some recent surveys about people's attitudes in climate change and how they prioritize climate change right now. And they are finding that people have lost interest in the issue of climate change. A couple reasons, because they're saying that COVID, people are so focused on that and surviving that and the lockdowns and the politics that go with it. They're also looking at like inflation in the economy and how that's getting them down. And they're talking about Russia and Ukraine, and people have no, our human mind can only handle so much stress. And so climate change is now at the bottom of, not the bottom, but it's dropped in priority because of that. Also, I think it's because people, what they said was people don't know what to do about it. And so that's one of the things I wanted to get across to you class today is like, what can you do personally? And we're going to get back to this. So think about these two questions. What can you do personally about your carbon footprint, about greenhouse gas emissions, about climate change? What is it that you can actually do about it? And then second, does it really matter? Does what you do matter? Does what you study matter? Do your small things that you can do at home matter with climate change? And I think that's one of the other pieces, like people have maybe given up a little bit on the climate change issue or allowing other people to take care of it for them. So think about that as we talk today for a few minutes on the next topic. I want to review just a little bit. So I saved this before we begin on a few of these first slides. So we, in the first couple of lessons that we've had, we have 4 total. This is the 3rd one. We talked about climate change, and we're all in agreement that carbon emissions are a problem, that it comes from our fossil energy, and that fossil energy is now responsible for about 75% of the greenhouse gas emissions, human-produced greenhouse gas emissions. And from that, we looked at transportation as 16%. So of this pie of emissions, here is the transportation emissions is right here, this pie. And we're saying that was 16%. That's a big chunk. Other things include buildings and industry and just energy production in general is emitting these greenhouse gases. But I decided to focus on transportation. We started looking at transportation then, and we said, you know what are our options? And we said biofuels. We talked a little bit about ethanol and biodiesel and how we are producing those fuels. Because they're a liquid fuel, they can replace petroleum directly in our fuel tank, so we don't have to change our transportation system. The second thing was we started talking about what if we changed our transportation to electric vehicles. And then we got on a discussion about electricity, because if we're going to have electric vehicles, we have to have more electricity to fuel those vehicles. Okay, so that's kind of where we're at. I think I have one or two more. Oh yeah, so then we talked about this perfect energy source. We all want that. What is the best energy source? And I think some of you asked me about what my preferences are. Affordable. It has to be reliable. That means it has to be there all the time. When I turn on my light switch, I need to find electricity there. It has to be sustainable. We talked about these energy sources: hydroelectric, wind, solar, coal, natural gas, and petroleum. We'll have a little bit more of that later. The one thing we did not talk about, and I know you're interested in, is nuclear energy. And I think that's a really interesting topic right now, and there's a lot of interest across the planet on how we can move to nuclear power quicker and what benefits that will bring. And I agree that there is a lot of benefits with nuclear power. One of the issues we have right now with nuclear power. So nuclear power, just to recap for those who don't understand it fully, we have uranium that is concentrated, and the reaction that it brings produces heat. And so that heat of the uranium in a reactor then produces steam, just like in a coal plant or a natural gas plant, where we produce steam using heat. It's a thermoelectric energy production. So thermoelectric, we have a steam generator, steam turns a turbine, turns a generator, and then we produce electricity. So that's the simplest form of energy, electricity production, is with that thermal production. Nuclear is no different than that, except the source of energy uses nuclear versus fossil fuels. One of the issues, if we talk about reliability of nuclear energy, 50% of our uranium comes from 10 countries. 10 countries is a lot, but if we think about all the countries that we get our fossil fuels from, we know the problem right now with Russia is Russia had about 5% of the global supply of petroleum, and that has caused a significant impact across the planet with energy prices increasing. So just one country having that much control over our energy sources is a challenge for all of us. If we look at solar and wind, every country, almost every place on the planet, we have solar and wind available to us. So we are not restricted by those who have that energy source. We have a 100-year supply of nuclear power, so that's great also. Sustainability, just a little bit on that. We think nuclear power is really good because of its greenhouse gas emissions, but we also know there's hazards with nuclear power. This recently in the Ukrainian war, Russia-Ukraine war, Russia took over a Chernobyl, which is an old nuclear power plant that melted down, had some issues there. People were really concerned about terrorism, wars, and how that could release more radioactive particles into the atmosphere and have a devastating impact. So there's some real concerns about the safety of nuclear. We also have to think about where we're storing that nuclear waste. We are mining uranium, and that is a hazardous mining situation that we have. So once again, I like nuclear power, but there are some issues that go along with that. We can't just say, let's do everything nuclear power right now. And one last slide of review is this affordability thing. We didn't talk too much about the cost of energy sources, but if we look at electricity and the cost of electricity, I'm going to look, this graph is a little bit busy, but these are the renewable energy sources here. And I'm going to focus on utility scale, so large scale solar systems in the US were about $30 to $40 per megawatt hour produced. This is low also, solar and different types of solar. Wind energy also down here at the bottom, so the bottom scale is the cost. As we go this way, it's higher and higher cost. So solar is actually pretty low, utility scale solar. If we look at solar panels on rooftops, because of the additional expense, we can end up with really high cost of electricity if we are going to solar panels on rooftops, which a lot of people like, but it costs a lot more money. If we look at this nuclear, here's our nuclear, the cost of a nuclear power plant is significant. It is more expensive than coal right now to put in nuclear power. Now these, I know this graph is complicated, I'm sorry. Down here is the cost of operating a nuclear power plant if we're not building it. So this is the cost of wind energy if we build a plant and operate it for its lifetime. This is if we aren't building a new nuclear power plant, but we're just continuing to generate electricity from that power plant. So right here and here is coal, 42 versus 29. So nuclear is super cheap to operate. Coal is cheap to operate, almost as cheap as the wind and solar, but solar and wind are actually really cheap energy sources right now. So keep in mind affordability. Which brings us to the topic of today, this electric grid, smart grid topic. There's just a lot of stuff to talk about here, but when we see these electric power poles, that's what we're talking about, this electric grid. One of the most important things that you can know about the power grid, electricity, unlike petroleum or gas, you can store that gasoline, and that will be there for you whenever you want to use it. When it's in your car, you have it there, you can use it whenever you want. With electricity, electricity is a secondary energy source. So we need something like coal or nuclear power to generate that electricity. That electricity is generated and it's used by a consumer. So I turn my lights on, I'm using electricity. But the important thing about this is that unlike gasoline where it's just there waiting to happen, we're talking about when I turn on my lights or my TV, somewhere a little bit more electricity has to be generated. There is no storage of electricity on the grid. If I need more electricity, somebody has to produce more electricity. So this electric supply must always equal electricity demand. And so that's really important. Now, this generation source can be farther away, not as critical, but we need to be generating power when we need it. And this is important. So what's happened over time for this electric grid to happen is we have, maybe this is a coal plant, and this might be a nuclear plant, right? Another coal plant, and we have, these are connected and they are generating electricity. That gives them a chance to balance all this supply and demand on the grid. So these are all our houses or schools or businesses connecting to this grid system. And as they're turning on their lights or running their computers, they are somehow getting electricity from the grid. And the grid is changing its power based on the needs of the people in that community. If not, we end up with a blackout, that there is no electricity. And that's a reliability function of our power system. People want to have electricity there when they need it. So part of this is, so now you have this generators, and then we looked at the power lines. These are the power lines going through, but to move electricity around the country or around the state or wherever you're at, you need to make sure it's an efficient way to transmit that electricity. Because we're transmitting electricity all the time, electricity will transport more efficiently at higher voltages. However, higher voltages are bad for people. That causes electric shock. It's dangerous to have that high voltage. So what we have are transformers in our electric grid system and happy workers that work with transformers, and they change the voltage from the generator. They will increase the voltage on those power lines, and then they'll have these large transmission lines, these large power poles that transmit high voltage power across a large electric grid. There is then transformers that drop the voltage back down to power lines that look more like this, that then can come into your house at 110 volts. These are maybe 150,000 volts. Sorry for my writing. Super high voltage, super efficient. And then when you get down here, it's low voltage, safer, but that's what comes into our houses. So our current grid system is a bunch of power plants, large power plants, transformers that put the energy on these transmission lines that might be hundreds of miles that they will transport this electricity. It then comes into a transformer in a neighborhood and then into our houses or businesses. So that is the electric grid. we look at, this is a grid in Colombia, and we are talking about miles and miles of high voltage, or kilometers of high voltage transmission lines coupled with distribution lines, hundreds of generators all working together to make sure that everywhere on the grid people have electricity. I think, if I am not mistaken, this is the area of Colombia that generates, has a potential to generate a lot of wind. And so this wind generation has to get transmitted there to Bogota or Medellin from long distances away. So that's one of the issues with any of our renewable energy, is that not always is this renewable energy available in where we need it, but it can be transmitted through power lines. The other thing that's, I think that the other thing about the grid that's important, remember, supply must meet demand all the time, but demand is changing. So if we look at throughout the day, this is a typical electricity demand curve in California, where we look at this x-axis is the megawatts that are required by the generating plants. And then this is the time of day. So over the course of a day, you think about people here are going to sleep at night and using less and less electricity as they're going to bed. Maybe the temperature in their house is changing, using less energy. They wake up in the morning and then they start turning on their coffee maker, making their eggs. And throughout the day, they're getting to the office, starting to use office equipment. Air conditioners go on because it's summer in California. Air conditioners go on, and then towards evening, once again, this curve starts dropping off again. So that's the demand curve that power generators have to meet. Let me see. So that demand curve, if we look at that, this is the same demand curve just in Minnesota. I did it just a couple days ago. I looked at this. This is our demand curve. Once again, in the morning, it starts ramping up, and then towards the afternoon, it's high. And this is actually in spring, so it's still a really dramatic increase in electricity needed and needed to be supplied by electric generators. On this side, I don't know if you can read the small writing, but we have a mix of electricity. In Minnesota, we use coal, natural gas, and wind primarily, but we also have nuclear. So this is saying that at this point in time, we have about 10% of our at this point of time, so anytime during the day, I can go online and look at how much energy is being generated. I know that over time, this has to change because we are using more and more electricity. Coal is a big chunk of it. We have natural gas as a chunk of it, nuclear and wind energy supplying our power. The grid operators, the people that manage the grid, look at the demand that's coming. They have predictions of how much demand they need, and then they will buy electricity from all these different energy sources. What's interesting also is that this same graphic that I can get from my electricity is showing that this is our wind energy supply right now throughout a day. And this black line, this is a 2-day chart, and the one before was just a 1-day chart. So this is 1 day, this is the next day. This is predicting the future of our wind. This is our solar system, day 1, and that prediction of day 2. And it's showing that unlike this demand curve, our wind and solar don't necessarily respond to when we need electricity, and that is a problem. We're generating wind power when we don't need it, or we don't have the wind power when we do need the electricity. We'll talk just about that, a little bit more about that in a second. We also know that demand curves are not consistent throughout the year. So if you're a generator of electricity or managing the power grid, you are seeing that this is our summer curve, where we had a peak of almost 120 120 megawatts that we needed to be generating. In the spring and the fall, this was between 70 and 90 megawatts. So a significantly more generation capacity is needed for a very specific time of day during the summer. So this is our peak demand in the summer is significant. And so how do we generate electricity to make sure our electricity is reliable all times of the year and all times of the day? What we're actually finding in the US right now is as we're moving towards more renewable energy, we are having a harder time with this peak demands because what happens with our nuclear plants and our thermoelectric plants, coal or natural gas, they ramp up to a certain amount of power generated and they don't easily drop off. They can't do this kind of curve in the middle of a day. Their time scale is much longer for ramping up electricity production and dropping electricity production. So that's a harder thing to match with that. And then we have the issue of solar and wind being a little bit unpredictable. They're coming online and or not available when we need them. Which brings us to then the smart grid. This is what the conversation is right now. How do we solve some of these problems with the smart grid? And this is the first, I have a couple of things that we're going to go through. The first one with the smart grid, what the smart grid will do is to help solve some of these problems with our energy system, is to take a look at this. Can we reduce this peak power? Because we know our energy suppliers, our electricity suppliers know that we need this much power somewhere on the system. And that has to include times when power plants are out for maintenance or something happens, something breaks and a power plant goes down. So we have to have this peaks power supply. We have to be ready for that. But what if we had some efficiencies that brought that peak power supply down even 10%? Now our energy system would have an easier time managing this peak because efficiencies like a more efficient lighting, more efficient television, more efficient refrigerator, where we're not changing our use, but we're actually reducing that peak energy demand because of efficiencies. It would actually drop this whole thing down with efficiencies. We'd be seeing this, which is super important to have that efficiency on the smart grid. Sorry, I'm going so fast. I get excited about this kind of thing. The next piece of the smart grid is called demand side management. They often refer to it as DSM. So remember this, look at this side first. We're going to look here, and I'm going to say that remember generation has to meet my demand. And so I am saying that my air conditioner uses 1,000 watts. My neighbor's or your air conditioner also uses 1,000 watts. Both of them are on about 30 minutes a day to keep my house cool. Right? We talked about more efficient air conditioners in the previous slide, but now it's like, okay, so now I have this really efficient air conditioner. I still have to run it 30 minutes every hour to cool my house down. What would happen if both of these air conditioners were running at the same time? This is 2,000 watts. So do you see that if we both use our air conditioner at the same time, I'm using mine, you're using yours, this generator guy over here has to produce 2,000 watts. Both of our air conditioners turn off because we only need them 30 minutes every hour. So now he has to go down to 0 watts. Stop producing power. Now I need my air conditioning again, you do too, so we're back up to 2,000 watts. So we see this cycling of our electric demand and the need to then cycle that electric supply. What happens if there is some smart technology that only allows that either will switch from my air conditioner to your air conditioner. So we both get 30 minutes. We just don't run our air conditioners at the same time. So now it looks like you're running yours, I'll run mine, you'll run yours, I'll run mine, you run yours, I'll run mine. And it's being controlled by this smart grid. So our devices in our home could be controlled to manage that grid. So now this generation is 1,000 watts and it's constant or more constant than this cycling up and down through the on-off cycles. So that's demand side management. Can we manage the demand to reduce this peak and to smooth out our energy needs? So that was number 2. We saw this grid picture before and how we have the traditional grid where we have a few generators and a bunch of people using the electricity. But what happens if we have a bunch more people producing electricity? This is a solar panel on my house. This is a solar panel out in a field. This might be a wind generator, another wind generator. We have solar, we have lots of distributed energy. So doing that as we move forward, this distributed energy system allows the electricity, it gives the grid operators, the electric grid operators, a bunch more flexibility in how they meet that demand. So we're once again all connected to the grid somewhere and they are managing all this stuff. But in order to do that requires a lot of sophisticated technology and computing to make sure that, oh, this was producing power, this solar panel on a person's house. That guy went on vacation, forgot to do something, and now that solar power is not available to us. How do we then fill in the gaps with all these other suppliers? So as time goes on, we are moving to more and more sources. Used to be just a few. Now we have multiple sources, which is good, but we also have to figure out how to manage that. So that's the third thing. Oops. Number 4, a larger grid system. So if I'm thinking about our energy use, this is me in Minnesota here, we have not as much sun up here as they do down here or over here. And so a larger grid system can allow solar production down here to be shipped all the way to Minnesota. The larger the grid, the more reliable it is. So my solar power is, or it's, the sun isn't shining today in Minnesota, but somewhere else the sun is shining, or some other time of day the sun is shining, they can then move this power into Minnesota. And so a lot of this is happening as the grid gets larger. We're moving electricity around further and further. So that helps with this smart grid technology, or a smart grid is needed to handle all this larger grid system. More transmission lines and more sharing of power. The final thing that this smart grid will be doing is looking at the addition of electricity storage. There's not a lot of storage on the grid right now because storage is expensive. I said electricity demand and supply have to meet each other all the time because we don't have storage on the grid. We're slowly building that storage, but it doubles the cost of electricity. So one of our pillars was affordability, but now if we add storage to that wind and solar power is not as affordable as it was in the past. So one of the most popular is pumped hydro, which means that we have a typical hydro dam, hydroelectric plant. We have this gravity, which we've created with water. And as that water drops, falls down, we are spinning a turbine, and that turbine is then generating electricity that goes out on the grid to our cities. Okay, so what if we have some solar power being generated or wind power being generated at a time when there is no, what's my wind turbine here? What if we're generating wind at a time when there is no demand for electricity. Now we can produce electricity that runs a pump, and it pumps the water back up to the reservoir where we can store it for another time that we can then release that water back down and generate electricity when we need it. So we are taking the electricity that's made from wind and solar when we don't need it, storing it for when we do need it, because storage is expensive. So we have gravity pump. That's primarily how we're doing it now in the United States and everywhere else. There's also a lot of discussion about batteries, lithium-ion batteries and other storage technologies. There's probably 100 storage technologies that are being evaluated right now. I just had my class. One of their assignments was every student had to find a different solar or a different energy storage technology and write about it. It's amazing how many new storage technologies are out there. So like I said, in a typical day, the solar peak like this here would happen about this time of day. So we'd see a peak in solar, but it's too early to match this peak of the day. So we keep this electricity from here and save it for this time of the day using storage. So maybe just a 4-hour storage of electricity that we can then shave that peak off and make balancing of the electric grid a little bit easier. So in summary, smart grid saying that we need to improve efficiency. We're looking at demand side management, so controlling our demand so it levels out the demand on the grid. We talk about distributed generation, multiple sources of electricity coming online, being generated, how we control that, a larger grid system, how we control that, and this electricity storage. So the smart grid is basically all the technology behind how we operate that grid system to make it more manageable, make it more reliable. So I want to go back to this original graph, affordable, reliable, sustainable. All these are linked together, and I'm going to look at what we've discussed so far. So affordability, we have fossil fuels are very affordable, very reliable. Biofuels are not as affordable, but fairly reliable. That is a fuel that we can store and use in a vehicle whenever we need it. Solar and wind, we're going to call them not as affordable because what I'm calling that when we have a wind energy that we can't count on all the time because we don't know when this wind is blowing or when the sun is shining. Those are called non-dispatchable. So non-dispatchable power. So they are affordable, but we also have to think about they're not always available. So yes, affordable, not reliable, which makes them a little bit problematic. Hydro is very affordable and it's very reliable. I think we're having a little bit of an issue now. There's some areas where there's a lot of hydro power, but because of climate change, they're not getting the rainfall that they hadn't needed in the past. And so that is no longer available to them, that hydro that they thought they were going to have. Nuclear, once again, expensive, super reliable. Oops. I'm going to pause with questions because I want to get back to transportation quickly. I think we have a few more minutes, and then I'll stop for questions. So back to transportation, that's where we left off, and then we had this whole discussion about electricity and how we do that. We talk about affordability of transportation. One of the issues with converting to electric vehicles to solve our petroleum problem, petroleum emission, transportation emission problem, is with electric vehicles. I actually own a Nissan Leaf, so I own an electric car. They are more expensive, so if I wanted to buy the car, it's $27,000 versus $16,000. That's the cheapest electric vehicle that we can buy in the United States right now. So when we think about affordability of converting our transportation system, electric vehicles are expensive to purchase. Now, over the life of the vehicle, because electricity is cheaper than powering those vehicles with gasoline or petroleum. So over the life of the vehicle, it's about equal, but most people don't have the money to invest in those cars right away. And right now, because it's a new technology, there's not a lot of used electric vehicles on the road. So it's a little bit more expensive, which keeps people from switching over transportation to electric vehicles. Also, with the electric vehicle situation and trying to solve our transportation issues, the energy density of a gallon of gasoline is 46 megajoules per kilogram. Where I look at a lithium ion battery, which is what's in these vehicles, these electric vehicles. This is a Tesla, of course, and it's charging using electricity. That's only 3. It's almost over 100 times less energy dense in those batteries as gasoline. That's 100 times more energy stored in the vehicle to travel down the road. So that's why these cars have huge batteries, and we still don't get the mileage, the kilometers per liter that we would in a gas-powered vehicle. So reliability means that we have to have a better infrastructure, because people want to jump in their car and go drive across country, and they don't have that right now with the electric vehicles. The last piece of this is vehicle sustainability, which we're talking about the operation of vehicles. So electric vehicle, if we operate it on the road, it's using electricity and is producing very little greenhouse gas emissions, very little water quality and air quality issues with the operation of electric vehicle versus a gas-powered vehicle. But then when we look at manufacturing, there's all sorts of things that go into thinking about the sustainability of a vehicle. There is greenhouse gas emissions with the manufacturing of a vehicle. There is water quality, air quality. We're talking about mining of the steel, looking at lithium and how we mine lithium for the batteries. We're looking at all the manufacturing that goes into these vehicles. So we're calling this a life cycle assessment. Life cycle assessment, I'm not calling it, that's the general term for how we evaluate whether a gas-powered vehicle or any kind of device one is better than the other in terms of sustainability. We can't just look at this tailpipe emissions for a car saying electric cars don't emit greenhouse gas emissions. We have to say, like, what happened? How was this car produced? How was the battery produced? Where was the raw material coming from? And how much emissions came from this? How much GHG came at this phase of the operation? When we were making that car, how much GHG emissions came from that? And we find out that actually in this phase of manufacturing and until the vehicle gets to the road, the electric vehicles have a higher greenhouse gas emissions than a gas-powered vehicle. But then when we get to here, these, of course, the electric vehicle is better on the road. When we talk about life cycle emissions, we also have to talk about this end of life. So the recycling and disposal of the vehicle, of the battery, of everything that goes into those vehicles. So looking at the sustainability in the big picture. Once again, all these issues of mining and batteries, we have to take into consideration. Bottom line is that with electric vehicles and gas-powered vehicles, greenhouse gas emissions are better with electric vehicles, and they're best when the electricity is cleaner. In Europe, this is a difference between a gas-powered vehicle and electric vehicle. More than half reduced greenhouse gas emissions. As we get to India, not much reduction. in converting to electric vehicles because all their electricity is generated from coal. You guys have a huge advantage. This is Columbia, and this is where I'm going to end it. You guys have a lot of hydropower, so you will benefit the most, much more than we will, for driving electric vehicles. So thinking about what we can do, back to that question I'm going to ask in a second, but conservation, meaning if we drove less, that's the best thing we can do for reducing our transportation emissions. We can make cars more efficient. That's the second thing we can do. And finally, we can look at alternatives. That is that renewable energy, biofuels, and electric vehicles.